It's a real pleasure to be here. It's a lot easier of a commute than going into the city because I actually happen to live here in Berkeley. So it's really nice to do this today. So I'm Angad Singh. I'm a trainer and I do customer support at Pix4D. So the primary, like my role is primarily doing workshops all around the country and doing private trainings. So essentially, I teach people how to use the software and how to implement drones into their workflows using multi-rate photogrammetry. And today, this is, I only have about 45 minutes or so. I'm a pretty casual person, so I want you to be very casual with me. If you have a question, please raise your hand and I'll try to address it as soon as possible. I think it's better to address questions as they come rather than at the end because it just makes it more of a conversation as opposed to me just standing up here and lecturing. In addition, if you want to go into a certain topic or learn more about something or troubleshooting projects, I'm more than happy to stay afterwards and get really nerdy with you guys. I'm more than happy to do that. I love to do that. And this is going to be a general overview of how the software works, what the science behind Pix4D is, and maybe some exciting things that are going to come in the future. So as a company, Pix4D was founded in 2011 by Dr. Christoph Streccia, who I personally find to be sort of like an intellectual idol. He's a really, really intelligent person who derived this company from his PhD work in computer vision. And this is sort of a revolution within the field of geoinformatics because it's only been around since this decade, really. And the implementation of this work hasn't really gotten very popular in industry until this year. So here we're at the forefront of utilizing images to extract information. And in terms of the company as a whole, it's about 100 people now, so it's pretty small if you compare it to more domineering firms like Esri, which has offices all over the world, and we're starting to do that. So we have an office here in San Francisco. Our main headquarters are in Lausanne, Switzerland. We have an R&D facility in Berlin, Germany, and in Shanghai we have a sales and training office. The reason that I bring this up is because a lot of you, maybe undergrads or doing your graduate study work, when you're done with your education, if you don't want to continue within the academic sphere, there are a lot of opportunities for geoinformatics out there in the professional world. And so Pix4D is always hiring, and we're more than interested in having passionate people that really are interested in this science and really interested in connecting with end users. So in terms of what do we actually do? Using 2D images, Pix4D provides mosaics, 2D mosaics, and highly precise 3D models. So you can take an image from any camera, whether that be an ultracam, that's 340 megapixels, loaded on the bottom of the airplane, or even the camera on your cell phone. You can create very highly precise and accurate 3D models with any image from any camera, as long as that image is of good quality. What we need to remember in this process is that the software can only reconstruct an area of interest or a feature of interest based on the image content. So you have to give it, it's good in, good out. If you give it bad data, it's going to give you bad data back. So just keep that in mind if you plan on using this in your work, or if you just want to have fun with it. Do you have a question?
Yes, how fine is the detail? And like, for example, could you photograph a picture of someone's face and recreate an accurate 3D
Absolutely.
Of that, or a body image also?
Yes, absolutely. If I took my cell phone out right now and took a video just walking around your head, I could create an extremely accurate 3D model of your facial structure and of your head in my software. In fact, I recently had a mountain biking accident and I had 10 stitches in my knee, which just came out recently. And I just took a couple images and put them in the software, and I have a really beautiful 3D model of the stitches. And then from that, if you create 2D maps, you can extract the elevation differences between the pixels for that. So you can really reconstruct anything. The whole idea is that you can reconstruct anything, and that's why it is sort of a revolution within the field, per se. So then how does this process actually work? Or first, let's talk about who's using it, and then I'll tell you how it works. So applications that are out there in the field, to be honest, it's kind of limitless. There are people that come to me all the time with projects that I'm just mind blown that people are doing that out there. In terms of geoinformatics, geophysics, GIS applications, you can create very high resolution 2D data sets that you can use for hydrology, general GIS application. You can create remote sensing data sets, essentially reflectance maps and with very small pixel sizes, high resolution. And then that's within the geoinformatics world. Out there in industry, construction is using this for logistical planning, understanding volumetric calculations. So you can fly over with a drone or take pictures with a regular terrestrial camera on the ground of a mound and calculate the precise volume of what that mound is. So if we look at applications like recently with Hurricane Harvey or with Irma, right? There's a lot of debris piles that are existing where they shouldn't be. So we can fly drones over these debris piles, calculate the precise volumes of how much debris is there, and then calculate how many trucks we need to take that out. In terms of police or accident reconstruction, we have a lot of clients that are in the public safety sector utilizing this for accident reconstruction. So you can have, if there's an accident on the highway, they need to document precisely what the scene looks like in order to take that information to court. So you can fly over the scene, you can create a highly accurate, precise 3D model of what's happening, and then put that 3D model that was produced with Pix4D into an accident reconstruction software. And within the accident reconstruction software, you can calculate the precise speeds at which the vehicles were entering, and based on the location of the debris or the locations of, if a bumper fell off, what was the velocity necessary for that bumper to travel the distance that it did. All of this information can be calculated within Pix4D. So on highways, when a highway is closed because of an accident scene, you can take 20 minutes, fly your drone, and clear the highway rather than having to go out there with a highly precise, survey-grade GPS or with a regular camera and document everything. So for me, that's in terms of public safety, I think that's a fantastic application. We have users in the film industries who will go in and let's say there's a beautiful house that they want to film a movie in, but they can only have access to that house for a short period of time. We can create highly accurate 3D models of what that building looks like, both the interior and the exterior. And then you can have actors going behind a green screen and then simply superimpose those actors that are on a green screen into this 3D model that was created within Pix4D. So at its core, Pix4D is a image processing and data production engine. What you use that data for is limitless, but you can produce it here. And for me, that's fantastic. So how does it actually work? It's based off a science called photogrammetry. In terms of what does the actual word of photogrammetry mean, it literally means making measurements from photographs. So this is in no way a new science. As soon as we had aircrafts that went up, people said, hey, let's put a camera, face it directly downward, and that kind of looks like a map. So traditional photogrammetry techniques, they take images and they stitch them together. But within Pix4D, we have to be careful about using the word stitch because we're not stitching anything. We're reconstructing the scene based off the image content. We're mosaicing. So that's why with multi-ray photogrammetry, we have to be careful about using the word stitching because that's the traditional word that has been around for 70, 80 years, as long as people have been taking photographs from airplanes. And this is all based on the fundamental concept of parallax. That is the displacement of objects based on perspective. So if we think about parallax with two cameras, this is, every single person here does this on a daily basis. Our eyes work like this, where we have two eyes that triangulate an object that we're looking at, and based off the perspective from both eyes and the concept of parallax, we can determine where that is in relationship to ourselves. Pix4D leverages this concept, but with a lot more cameras. So if you have two cameras, imagine that these are your eyeballs, you're looking at a tree, this is the general vicinity. The red arrow ellipsoid here represents the general vicinity where that tree physically is located in space relative to yourself. So that's with our eyes. This is not highly precise because this general vicinity has a long error in the length dimension, right? We don't know if it's 5 feet away or if it's over here 10 feet away. Most of us probably do, but in terms of the example, you're not highly precise on that. So within Pix4D, we leverage multiple cameras. It's the idea that if you add a third perspective, or a fourth perspective, or a 20th perspective, you can triangulate based on all of those cameras the position of some object or feature of interest in three-dimensional space. With the addition of more perspectives, the error or the extent of the area where we believe that 3D feature to be gets smaller and smaller and smaller. And that's the fundamental concept behind Pix4D as a software. So it's called multi-ray photogrammetry. We're leveraging very high levels of redundancy in our image content, meaning a significant level of overlap, so that we can reconstruct three-dimensional points in relation to millions or hundreds of millions of other three-dimensional points, which is why this technology is relatively new, because the level of computing power required to process these data sets is truly immense. They can take hours and hours, or even days, depending on the number of images that you provide the software. So if we, and it is a pretty automated process as well, based on improvements in machine learning and improvements in computer vision. So if we think about it, the images can be of any camera, but they have to be of good quality because the software can only reconstruct what it can interpret from the image content. But what's extremely important is that the images have a high level of overlap. For any data set that you give this software, there should be a minimum of 75% overlap in the front direction and 60% overlap in the sides. So all of the features on the ground, or a distinct point on the ground, is going to be able to be viewed in a minimum of 10, 15, maybe up to 20 to 30 images. Right? Every image that we add another perspective of where that image is located relative to all the other image locations, which enables us to better triangulate that location in space. So how does Pix4D actually work as a software? You provide it with image content that has been taken in very high, overlapping fashion. And we scan, the software will go through and it will scan every single image and determine what we call key points. Key points are unique textures, right? So if us as humans, if we look at this, we may say, oh, a unique texture is this red car. But notice that the software didn't calculate that that's a unique texture, because unlike humans, where we think of additional aspects such as geometry, color, to determine what is unique, what is different from the rest, the software bases it on a multitude of different parameters, such as color and geometry, but on such a fine pixel level that it can define these key points, these unique areas, as unique textures. And precisely what a key point is, beyond that definition that I provided, is a little fuzzy, because that's sort of proprietary. But at the same time, it's something that I have been seeking to find out since I joined Pix4D.
Can you do it on black and white
Yes,
imagery?
you can do it on black and white imagery. The precision of black and white imagery will be slightly less because we're lacking those dimensions of color that we would have in RGB images. But yes, it can be done with black and white imagery, which is how multispectral information for remote sensing is mosaicked. Because those bands are panchromatic in terms of they don't have RGB values, they only have one of those.
So is this unique texture of more than one pixel that goes into defining, or is it pixel based?
Well, it is certainly pixel based, but it's a multi-dimensional filter. So it will go through the size of that filter, whether that be 9 by 9 pixels, 8 by 8 pixels. That's uncertain because it doesn't. We call it a pyramid structure. So it will go through with a filter of a particular size and based off a number of internal parameters calculated on a pixel by pixel basis, it will determine what is not a unique texture. So it is very multidimensional and very complex. And a lot of this information isn't readily available. This is something that even myself, I've asked Dr. Streccia, the CEO of our company, what is a key point? And he started to explain it, and it becomes so complex that he kind of realized, oh, I don't want to spend an hour just telling this guy what a key point is right now, because it's important. And yes, for me, it's a huge curiosity. What is this? Because the whole software is based off key points, but all we need to think of them as unique textures.
Do you need picture, or do you need
data about where the picture was taken, or is that all done with overlaps? Does the software decide where a picture is?
I'm about to get in that.
Okay.
I'm about to, yeah. But it can be both. Yeah.
With regards to key points, how does it, do you run into issues like in the first equation measurable, like when you can opted on this picture?
Absolutely. The software finds it significantly more difficult to construct key points if the surface is very homogeneous, right? So if we have, let's say, a large slab of cement, there's a lack of texture, a lack of contrast in its color and its shape, and therefore we find it more difficult to reconstruct these areas of interest. It's not to say that very homogeneous regions are impossible to reconstruct. It's just that the output pixel sizes will be far greater because there's more interpolation in terms of how do we reconstruct that area of interest. For example, water is one of the most difficult, if not impossible, features to reconstruct because, one, water is very homogeneous, it's the same color pretty much. Two, it has a dynamic surface. Water is not static, so because it's moving, what the software may calculate in one image as a unique texture or a key point will not be in the same location in the adjacent image because the surface is moving. In the same way, water is also highly reflective. So if you're looking at water from where I'm standing now, and then I take 3 steps over, that same location, because of the highly reflective surface type, will appear different. And that's why water is impossible to reconstruct. In terms of, a lot of you may be working with vegetation, we need to keep in mind that vegetation is one of the hardest regions or surface types to reconstruct because of wind. If you have tall grass or plants, the tops of those plants are going to be moving, even with a little bit amount of wind. So a key point in one image will not be in the same location as the adjacent image. And so it is not to say that these surface types are impossible to reconstruct, but they're harder.
Is there an opportunity to incorporate like fluid lensing dynamics into this?
Possibly down the road, but not based on the model that's being utilized right now. And I'd be very interested to talk to you about that afterwards. Absolutely. Any other questions on this, or can I go forward?
You mentioned moving traffic is a problem. You have like a freeway.
So a freeway is not a problem in some ways because the cars are moving, so their key points won't be in the same location in the images. So the software simply will not reconstruct that. So it will go away. So next, after we've calculated key points in every single image, we match those key points with the same key point in the adjacent images. And we call these tie points because they're literally tying the image content or tying that unique texture or unique characteristic together. So, as we can see in the previous slide, there's a lot of key points, but not all the key points become tie points, right? So when we create tie points, we can then create essentially a sparse point cloud where there's 3-dimensional points existing all over. And that's what tie points would be. So in terms of how does it reconstruct it, so typically there would be 3 ways to do this. The standard default way that Pix4D reconstructs an area of interest based on the image content is purely based off the spatial relationships that are inherent to that image content based on parallax, based on multiple perspectives from the high level of overlap. So if we have a 5-foot tall griffin, we as humans, we know when we see this in real life that this is a griffin and it's 5 feet tall. The software has no idea what is up, what is down, what is left or right. The software has no idea what is the distance between the eye and the beak. All it knows is a specific ratio based on the spatial relationships from the image content. So it understands that there's, that the ratio from the eye to the corner of the beak is X, and the ratio from the top of the wing to the bottom of the wing is Y. It has no idea what the dimensions are. It has no conception of what this would be in real life. So you can have 3D models where you'll have properly ratioed or the topologies are correct, but they will not relate to the real world. So to do that, we georeference. So all of us from the GIS world know it's georeferencing. So essentially, georeferencing is to tell the software where this exists in real life. It's to provide position, orientation, and scale. So typically, the first level of georeferencing, of absolute georeferencing, comes from the image geotags. That is the GPS coordinates that your drone takes when it captures these images. But the commercial grade GPS in the majority of drones today is only precise to 3 to 5 meters in the X and Y or in lat long, and up to 10 meters of error in the Z axis for elevation values. So yes, you can absolutely georeference your data sets simply relying on the GPS coordinates in your images. But if you want survey grade accuracy, if you want 1 to 3 centimeters of accuracy, you need to give it known locations, and we call those ground control points. So essentially the way that workflow works is here in this image, all the blue dots, they represent the GPS location where that image was taken. But these green circles, these represent highly precise GPS measurements that were sampled throughout the project area. So with survey grade instrumentation, those are total stations, differential GPSs, RTK GPS systems, essentially very highly precise and accurate GPS systems. You will go through your project area and collect measurements over targets. And then when you reconstruct the project in the software, you can go into these targets and you can say to the software, the exact center of this target is related to this GPS point. And then it will position, orient, and scale the entirety of your data set to those highly precise GPS targets.
With the applications that are maybe indoors and there's like some other subject matter, can you deploy some type of known quantity marker to
Absolutely.
get the exact size of the subject?
Yes, absolutely. We would call that relative georeferencing because it's not absolute in terms of where it exists precisely in the world, but the scale and the position would be correct in the vicinity of where that what we call scale constraint. So essentially, let's say you're reconstructing this room, we can measure the dimension of this table and then tell the software that this table is X, and it will position and scale the entirety of your data set, that whole 3D point cloud, to the dimensions of the table. So yes, a lot of public safety workers are doing that. So when police do accident scene reconstruction, they throw a triangle on the ground that they have no dimensions, and they tell the software that what the dimensions are, and the software will then will scale and orient the entirety of your data set to that known scale. So are there any other questions on accuracy? For when we teach our classes, or when I teach the classes that I teach, this is one of the most important subjects because in the real world, a lot of land surveyors are utilizing this software as a new technology, and for them, precision and accuracy in terms of its absolute georeferencing is highly important.
Are you going to show us what the targets look like?
No, I didn't have an example of a target, but on the most basic sense, it would be a square with an X. A square with an X. But you should be able to determine the center pixel of that X at the pixel level. And if you want to know more, afterwards we can definitely talk about targets. The easiest way to get targets is to Google aerial targets or land survey targets and buy them off Amazon. You can get them for like $3 a target. So then, after you do the georeferencing, after you've gone through all the images and created tie points, we create, after step 1 of the software has 3 steps, 1, 2, and 3. After step 1, we create a sparse point cloud. So all of these on the top, these green and blue orbs, represent where the images were taken. The blue orbs represent where the GPS coordinate of that image is in space. And then the software goes through and it fixes for 8 internal variables of your camera and 4 external variables of the camera. So essentially, what's the exact tilt? What's the exact orientation of where the images were taken in relation to all the other images? And then internally, every camera is different. If you drop your camera, the sensor within your camera is going to shift on just a very little amount, but that very little amount really does matter. And that's why it's important that we solve for all these 8 internal camera parameters. And then essentially, this sparse point cloud here represents all of the tie points. So these are all the tie points. But then that's pretty sparse. I mean, it's called a sparse point cloud. So that's not great. You can't really give that to a client, or you can't really use that for much. But it is the infrastructure of the entirety of your data set, and it's incredibly important that this is created correctly. And then after you get your sparse point cloud, we go through and we create what we call a dense point cloud in step 2. So a densified point cloud is millions of discrete points. They're not touching each other. They are individually discrete points. Essentially what we do is we take the sparse point cloud, and then from the image content, we interpolate pixels between the sparse point cloud in a manner that it maintains the inherent spatial relationships. So we create that sparse point cloud, the infrastructure or the chassis of your data set, and then we pull pixels from the remainder of the image content to fill it in. But they're discrete points. It's not very pretty because there still may be holes. So in order to address for some of those holes, we create a 3D textured mesh. Essentially, there's a chair here if you'd like a chair. So we create a 3D textured mesh where we interpolate triangles to fill all the voids between these discrete points in the densified point cloud. The densified point cloud is similar to what a LiDAR machine would create, except for the densified LiDAR is laser, so you're using laser, but here within Pix4D we're using photogrammetry, which is image content or just photos.
And also the point that this is so many more points than the LiDAR, right?
Yes, that is also true. This is millions and millions of points depending on what you're reconstructing and the resolution of your camera. So it's important that we have these two data sets. This is your highly accurate 3D model.
Do you have any extensions like FBX or something for like VR ready? So I can just put it in like a gaming engine?
We don't. These are the only currently available formats. But I mean, you can always export. You would probably want a 3D textured mesh for your VR setups, and you can simply export a FBZ or even an OBJ object file, and then convert it in another third-party software to put in your third-party software. If you would like a particular file format, please tell me after the class, and I will write suggestions to the developers. That's also a really big thing within Pix4D, is we practice what we call agile software development. So our user base will tell us that they want certain features, and we put them in a queue that our developers look at, and then they comprehend whether it can be put into an iteration of the software that's coming out shortly or in the long term. So it's very important to us that our users are being able to get the file formats and the types of outputs that they desire. So I can absolutely tell the developers if you have a particular file format.
On the subject of LiDAR, can you use LiDAR to increase the accuracy of this, or is it more accurate than how LiDAR can get you?
There are quite a few firms out there. A lot of them happen to be here in the Bay Area, Silicon Valley, that are using LiDAR and photogrammetry together to create extremely precise point clouds. A lot of times they're using them for simulation study or training data for autonomous vehicles. And so yes, there are people out there doing that. How do they do that? I don't know, but they are doing that. And so these are your two basic 3D models that you can output from within Pix4D. And then after you take your 3D model, if you take your 3D, your densified point cloud, and just set all the z values to 0, it snaps everything together, and you have what we call an orthomosaic, a highly precise 2D map where there's no perspective, where distances and direction are constant. I think this is amazing. You can utilize very highly accurate orthomosaics. For example, if this is georeferenced properly with survey grade instrumentation, you can do distance or area calculations down to whatever the accuracy of your data set is, usually within a few centimeters. And so you can calculate what the precise length of that road is. Or you can calculate what the precise distance of an opening is. So for construction, they can determine, hey, we can take a truck through there, it's big enough, or no, we can't. We need to break something. And so that's what you get. You get an orthomosaic. For logistical planning, it's a very highly accurate two-dimensional map. So are there any questions on orthos? They're really cool. I like them. Next, outputs, digital surface model. So for those of you in the GIS world, you know what a DEM is, right? It's a raster data set. So what that means is you have a data set where each pixel has an X, Y location for where it exists in space relative to all the other pixels. And then inherent to that pixel, there's a value that is indicative of elevation. With a surface model, we're not really giving you, or with a DSM, we're not really giving you elevation. We're giving you what the highest visible point is at space at that location. So we're giving you a precise representation of what the surface looks like, hence digital surface model. We have a really cool tool, I think it's cool, called, it's the DTM filter function. So we also output what we call a digital terrain model, where it's a more homogeneous representation of what the ground looks like, based on, first, filtering through the DSM, and based on a threshold of slope values, by pixel to pixel, we can determine what should be there and what should not be there. And then we go and we remove those objects that we determine should not be there, and then we interpolate based on the adjacent pixels that are remaining, what the values would be for there. So essentially, here we have buildings and trees, and here we don't. So it's a great filtering function that exists. Is it perfect? No. Is it really good? Yes. It'll get better in time, and I'll show you how it's about to get better in a moment. But DSMs and digital terrain models they're really good for getting micro level analysis of what's happening on the ground. For me, that's one of the most important things of this technology, is that before, when we pulled remote sensing data from satellites, or when we're pulling GIS data from in vector files, we're able to do macro level analytics, but sometimes the precision of our micro level analytics is not always there. And with technology like this, where you can get pixel sizes of 1 centimeter, 2 centimeter, you can really provide very valuable insights on the micro level. And then additional outputs that you can get from Pix4D, you can take your orthomosaic and export it as Google Tiles or a KML file, or you can zip them together as a KMZ folder and throw that onto Google Earth or Google Map and overlay what your data sets look like over what the Google Maps data set looks like. You can create contour lines, which are really important for land survey and construction industries. And then in terms of, a lot of you may be doing remote sensing analytics, you can export reflectance maps. For me, I came from a remote sensing background. So for those of you who may not know what reflectance is a unit between 0 and 1, or essentially it's a percentage of how much light is being reflected at a certain pixel in space in a particular range of the electromagnetic spectrum. So RGB is how much light or color is coming out in the red wavelengths, in the green, and in the blue. So on a rough level, that's basically what reflectance maps are. But for me, when we can do absolute radiometric calibrations, which means that if you have a multispectral camera on a drone or even just on an airplane, every time it takes a photo, there'll be a sunlight sensor. And that sunlight sensor will calculate what the exact irradiance of the sun is at that given moment, and what the exact angle of the sun is at that given moment, and calibrate it absolutely for the entirety of the data set, so that you can compare reflectance maps from one time period to another time period, instead of having it be relative to what was happening on the ground right there and then. For those of you who study remote sensing, we know that it's an extremely variable science that is really dependent on the environmental conditions at the given moment. I can talk about that for a long time. So if you're more interested in that, we can go on. And then index maps. You can create your vegetable indices just to compare different wavelengths within your reflectance maps. So in terms of, it's just great that Pix4D can do absolute calibration for reflectance. I think that's really great. And then what's coming next and what is really cool. So Pix4D as a company, we find it really important that we continue research and we don't just create a product and sell it and make money off it. That's not the goal. The goal is to be an academic-centered company where we're continually doing research, where we're continually engaging with the academic community so that we can really push the limits of what the technology and what the software is encountering at the given moment. With the integration of machine learning, we can really push the boundaries of classification of our data sets. So with LiDAR, with laser, when you fly over an area with LiDAR, they take the point cloud that is derived in that LiDAR machine, and they can classify it into 6 different groups. Basically, based off the geometry of those points in relation to each other, we can say this is a car, this is a building, this is crop, this is a road. With photogrammetry, we haven't been able to do that yet. And this is coming in a future iteration of the software, hopefully within the coming months, where we're not only using geometry of the point cloud, but also color information to classify what those points are. So if you can say, okay, these are all cars, and we can continually train that data set using supervised machine learning techniques, then we can really, with a very high precision, upwards of 98%, classify the points in the point cloud for your given need. So you can create your own training data where you're taking multitudes of different projects, going in, the software is classifying what those points are, you're telling it yes or no, that's correct, and then the system keeps training itself. And when you can do that, and the system can keep training itself, it gets better. It keeps learning the patterns that are inherent to the point clouds, and it learns how to better classify what's happening on the ground. And then you can say, okay, for the DTM, for the digital terrain model, I want to remove all the cars. And based off automatic point cloud classification, with a higher accuracy, we can remove points from that point cloud. So for me, I think that the integration of machine learning techniques into what is already such a really intriguing workflow is going to make it better. And so you can get even more valuable insights from your data. And at the end of the day, that's the most important part. What's the point of creating gigabytes and terabytes of data if it doesn't mean anything or you can't do anything with it? So that's what we have from there. Any questions on integration of machine learning? Or what I do want to say about this is, if you go to pix4d.com and use pix4d.com/research, all of the academic papers that have been published by the company or by people within the company are available for you to download and read. A lot of the data sets that we use for this training are available for you to read there. A lot of this information, some of it's proprietary, such as the exact definition of a key point, but the majority of it is not. Because if you can utilize some of this research to further your own research, or to further information in terms of data science, that's fantastic and all of us benefit. So that's why all of our white papers are available online, and our data sets.
So before we learned to set the white balance setting on the camera to a manual setting, we had issues with a number of images with automatic white balance, and the cameras trying to adjust and get the right color tone.
Yeah.
Does Pix4D, I know there's some color matching.
Yeah.
Could you talk a little bit more about that, and if there may be some pre-processing tools that we could do to get a more consistent?
So in terms of you're creating an output map and there's problems with the color, right? So this can happen a lot of times around water, where because of the highly reflexive characteristics of water, images that are taken in the general vicinity of that will appear slightly darker or lighter depending on what the wavelengths of light coming are and what the camera or your sensor interprets it as. Pix4D doesn't color balance for our orthomosaics today. We may in the future, I don't know. But in terms of the reconstruction, the software reconstruction purely based on the data that you've given it. We assume that you've given it good data, because why would you give it bad data? So
I think bad data would be like took shots at multiple times of the day at the same spot.
Yeah, precisely. That is very bad. Because the shadows are going to be in different regions. You want to capture your data, you want to capture your images as close together and at the same time as possible. Now, depending on the exact time of day when it's best to capture aerial imagery, there's a lot of debates on that, but in terms of what actual lighting conditions you want, we call it flat light or diffuse light. If it's a nice overcast day and there's no shadows, that is perfect. Go up there and collect as much data as possible, because it's going to be good.
I've heard that using a fixed f-stop on the camera can be good for photogrammetry. Is that true with your software?
I'm not particularly sure.
What I mean, like 122 or whatever, f-stop on SLR camera?
I'm not sure, but I bet we could find you an answer. But in terms of filtering, so a lot of times people will ask me questions in terms of, oh, if I add this filter, or if I do this image processing technique to fix the data values before I give it to the software, we always advise that you don't do that, right? I mean, if you're very specialized and you understand exactly what you're doing on an empirical level to your images before you give it to the software, that's fine, and that's great. But you want to be careful about changing some of the values before you give it to the software, because if additional algorithms are added to the images before we, add our own algorithms on top of that, you're just increasing the potential for error. And so we need to be careful with that. But
so like the rolling shutter of a GoPro, is that okay?
Oh, okay. So that's great that you asked that question. Do you guys know about shutter models? So there's two commercially available shutter models on cameras. One's called the global shutter, where all of the pixels in the sensor are triggered at the exact same time. So basically the exposure opens, all the light comes in, captures it, and it closes. Then there's what's called a linear rolling shutter, where the rows of pixels are triggered at different times. So the first row of the camera will capture data, then the next row, then the next row. Essentially, it's cheaper for camera manufacturers to do that, and some videographers argue that it's better for video. But in terms of still images, it's not the best, because if objects on the ground are moving faster than the speed of your shutter, there will be geometric distortions in what it looks like. So next time you guys are sitting on an airplane or you're driving down the highway with a car, if you're not driving, take out your phone and take a picture. The propellers in that image, if you're taking a picture of an airplane, will appear curved, even though we know them to be straight. Same thing with buildings or signposts. If you're driving pretty fast and you take a picture of a signpost, it may not appear straight. It will appear at an angle. And that's due to the effects of the linear rolling shutter, where from the time it takes the camera to write the data from the top row of the sensor to the bottom of the sensor, we've introduced a skew. So it does affect it. Pix4D has a linear rolling shutter optimization tool where if you're taking your images with a camera that you know has a linear rolling shutter, we will fix for that, but you need to tell the software that the linear rolling shutter is the camera model that you're using. And as drones get more bigger, bigger in terms of more widespread usage, more camera manufacturers are starting to go towards global shutters, just because, once again, if you add more algorithms than you need to, every time you do a process and skew the data, change it a little bit more, you're just always adding more steps, and more steps possibly mean more error at the end of the day. So we fix for it, but it's important to know if you're flying drones, what type of camera model you have.
So two quick questions. Is there an academic license? If not, what's your business model? And is this a web interface or is it on a local machine?
So we have both in terms of cloud or the desktop processing. You can process on your computer or you can process on the cloud. Either way. At this day and age, you get more control over your data set if you process on a local machine. However, we know that this is a really big, read-write intensive process where you need really powerful computers. And if you just don't have the computing power to do a project, you can send it to our cloud and we'll process it for you and send it back. So you can do it both ways. In terms of academic licensing, yes. Actually, I was told to tell you guys all this today. We just released a student license for $99 a semester.